Okay, we're back again with a video for section 7.2, sets. We finished off chapter 3. So we'll start with the definition of a set. That's problems 17 through 22, and then we'll go into some notation, problems 1 through 8. Union, intersection, and complement are three important aspects of dealing with sets, problems 9 through 16, 23, and 24. And then Venn diagrams, problems 25 through 36 and 67 through 78. Keep in mind when you're doing the homework that these sets of problems, 25 through 36, deals with one particular Venn diagram, 67 through 78 deals with another, so those actually aren't quite so many problems as they look like. So what is a set? Well, it's a collection of things. It's kind of a vague idea, but we just need to be able to talk about, having a bunch of things together and breaking them up into different parts. And so sets are usually stated either as a list or in terms of a property. So since baseball season is starting soon, we can say Twins starting pitchers in 1987, right? That's a collection of, people in this case. And we can say that was Bert Blyleven, Frank Viola, Les Straker, not Phil Niekro, but Joe Niekro and Mike Smithson. Right. And so what do we have? A name for our set, Twins starting pitchers in 1987, equals, sets are usually denoted by these curly braces, and we have 5 people in our sets, these 5 gentlemen, Blyleven, Viola, Straker, Niekro, and Smith, and we just list them. Right, so that's an example of a set given as a list. Sets can also be given as a property. Right, so we can say, what is the set of all great Twins pitchers? So there's a name for our set. Oops. And since it's a set, we put a little curly brace there. And this can be all Twins pitchers with wins with the Twins greater than or equal to 100. Right. So when we give a property, when we define a set by properties, we give it a name, as always, equals, and we give a collection of people that we're actually interested in. So all pitchers with the Twins, and we only want some of them. We want some that have this particular property. They won 100 games with the Twins. Right? So this is called a universal set, and this is the collection of people from this set that I want to pick out. So you think about the list of all the Twins pitchers, and you pick out the ones that have won 100 games. So sets can often be given as a property, like that, or as a list. There's only a couple of pitchers who've won, 5 again, 100 games with the Twins. So Jim Cott, Bert Blyleven, Scott Radke, oops, don't want to spell that, Jim Perry, not Gaylord Perry, and Frank Viola. Right. So here's a list, here's a property. There are different ways of saying the same thing. This is all the pitchers who've won at least 100 games with the Twins. This property corresponds to that list. Sometimes properties don't work. We get something called the empty set. We could say, let's define a set, greatest Twins pitchers. And we'll call that, out of all the Twins pitchers, right, we want the ones that have wins with the Twins at least 200. Right? So we need a list of all the pitchers who have won at least 200 games with the Twins. There are none. And there's never been a pitcher who stayed so long with the Twins and been really good, and the Twins have been good, so they could get at least 200 wins. So we actually have a notation for this occurrence. Here's the name of our set, which we want it to be a set. And when it turns out there's nothing actually in the set, there's nobody who's got this property, we write this symbol. It's sort of a 0 with a dash through it. It's the Greek letter phi. Or you can write a bracket, right, that denotes a set with nothing in it, right? So instead of having a list with a bunch of people in it, right, there's nobody there. This is called the empty set, the set with nothing in it. And you get that sometimes when you're trying to define things in terms of properties, because sometimes there's nothing that has that property. Okay. Slightly more mathematical example. Suppose A equals the set of all real numbers, x, so that x squared equals 4. Right? And so this is how we construct a set. Right? Curly braces tells me that it's a set. I have some universal set, right? I'm only interested in real numbers, and I want real numbers with a particular property. If you square them, you get 4. And we know what numbers those are. 2 and 2. So 2 different ways to give the same set. Give a particular property of them, x squared equals 4, or you can just list them, minus 2 and 2. We can also say, suppose we want all real numbers that solve the equation x squared equals minus 4. Well, there are no numbers, right? Square root of minus 4 is imaginary. And so that gives us our empty set. Right? Or just no list. So, sets you can say by properties, or you can say them by listing them. And there's some specific notation for when you have a property that nothing actually fits. So, we've been dealing with sets, and we want to talk about what's inside a set and collections of things inside a set. So subset and element. An element of a set is just one of the things that's in a set. A subset is a collection of things that's in a set. So if we go back to our list of great twins pitchers, right? Cott, Blyleven, Radke, Perry, Viola. If we just pick one of them out, Radke, for example, so Brad Radke is just one of the things in the list. So he's a great twins pitcher. He's one of the people in the list, and we have a notation for that. It's an E, but sort of drawn as a sideways. I mean, it's actually the Greek letter epsilon. So it's an element of the great set, the great twins pitchers. If I pick more than one of the things that's in the set, so if we go back to a great twins pitchers, and suppose we say, okay, we want to talk about Cott and Blyleven, right? These are the two that pitched in the 70s, for example. Well, Perry pitched in the 70s too, but we'll go with Cott and Blyleven. Well, the set that consists of just Cott and Blyleven that's what we call a subset of our collection of great twins pitchers. Why? Well, this is a set itself. We can call it a set B, right? It's got 2 elements in it, and there's a short list, and everything in that set is in this set, right? So Cott and Blyleven are both in that set. So we're just picking out more than one thing. So a subset is just a sublist or a collection of things from the original set. And we have notation for that too. The set that consists of just Cott and Blyleven is a subset. That's a C, sort of an elongated C of the set of great twins pitchers. Okay. Now again, a more mathematical thing, sort of involving numbers, right? If A is a set that consists of the numbers 2, 3, 5, and 6, then 6 is an element of A, because 6 is in the list somewhere, but 10 is not an element of A, because 10 is not in the list for A at all. So, if we set B equal to the set 2, 3, 5, then B is a subset of A, since everything in B is in A. So B is a subset of A. If we set C equal to the set 2, 3, 10, then C is not a subset of A. 2, that's an A. 3, that's an A. 10, not an A. Right? And so if a set has even one thing that's not in the other set, then it can't be a subset, because they differ somehow. So a subset is just things, a sublist, right? A collection of some of the things in A, but not necessarily all of them. And the symbol for that is a little subset thing. It's a C that goes sort of sideways. Okay. Intersection and union. So the intersection of two sets is all things that are in both sets A and B. The union of two sets is things that are either A or in either A or B. Intersection, think and. Union, what is union? Union, think or. And when we say either or A or B, means A or B or both. So, suppose I have two sets, A, and we'll just go with numbers here, 2, 3, 5, and 6, and B we'll call 1, 5, and 10. That's a 5. Okay, so what is A intersection B? The symbol for intersection is an upside down U, and that's everything that's in both sets, right? So 2 is in A, but it's not in B, so it's not in the intersection. 3 is in A, but it's not in B, so it's not in the intersection. 5 is in A, 5 is in A, 5 is in B, excellent. So 5 is in both A and B, so it's in the intersection. 6 is in A, but not in B, so that's not in the intersection. 1 is in B, but not in A, so it's not in the intersection. 10 is in B, but not in A, so it's not in the intersection. So the intersection of A and B is just the one thing, 5, because that's common to both of them. What's A union B? Well, the symbol for union is a U. A union B. And here you just list everything that's in both of them. So everything that's in A, 2, 3, 5, 6. And everything that's in B, 1, we've already listed 5, so we don't need to list it again, 10. So there's our union of the two of them. So it's everything that's in either one or in both, right? So 5 is in both, so we list it, but we only need to list it once. 2, 3, 6 are in A, 2, 3, 6, and then 1 and 10, we throw those in there. Great, if we set C, if C equals 12, 14, 18, then what's C intersection A? Well, what is everything that is in both C and in A at the same time? Well, 2 is in A, not in C, 3 is in A, not in C, 5 is in A, not in C, 6 is in A, not in C, 12 is in C, but not in A, 14 is in C, not in A, 18 is in C, not in A. There's nothing in both of them. So that's the empty set. There's nothing in the intersection. And this is our notation to say there's nothing there. Okay, so intersection, you're only looking at things that are in both at the same time, in both lists. A union B is everything in A or everything in B. Just take both lists, throw them together. But don't double count anything. 5 is in both. So you only need to write it down once. Okay. Complements and universal sets. So if A is a subset of some other set U, then the complement of A is all the things that are in U that are not in A. So, let A be, well, we'll just stick with our same set, 2, 3, 5, 6. U equal to the set of numbers 1 through 10, integers 1 through 10. So there's our set U. Here's another set A. Is A a subset of U? Question mark. Well, 2 is in A and it's in U. 3 is in A, it's in U. 5 is in A, it's in U. 6 is in A. 6 is in U. Yes. Everything in A is in U. Okay. A prime, so you can read that A prime or A complement. What's that? That's everything that's in U that is not in A. Right? And I suppose I should have capitalized that. Not. That looks like a watt. N-O-T. So complement goes with the word not, just like intersection goes with the word and, union goes with the word or, complement goes with the word not. So what is A prime? Well, 1, that's not, it's in U but not in A. 2 is in U but it's also in A, so we ignore that. 3 is in A, so we ignore that. 4 is in U but not in A. 5 and 6 are in A, so we ignore them. 7, 8, 9, and 10 are not in A. So A is everything 2, 3, 5, 6. Then what's A prime? It's everything that's not in A but is in U. So 1, 4, 7, 8, 9, 10. So a couple things to note about A and A prime. A intersection A prime? Well, what's that? Everything that's in A prime is by definition not in A. So is there anything that's in both A and A prime? Nope, that's the empty set. A union A prime. What's everything that's in A and also, I shouldn't use and there. What's everything that's in A or in A prime? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Everything in U is in either A or in A prime, right? Everything in U is either in A or it's not in A. And so A union A prime is the entire set U. Okay. So, and that brings us down to, I think that brings us down to Venn diagrams. Oop, and I forgot to say which example this is, but that's okay. So, suppose we have 200 Math 196 students are surveyed. And in this particular survey, they are surveyed about ice cream. So 170 of them like chocolate ice cream. Ice cream. 130 like vanilla ice cream. And 120 like both. And then there's all sorts of questions we can ask about our survey of students. How many like vanilla but not chocolate? For example. Right? Or how many like chocolate but not vanilla? How many just don't like either one? So, a little bit bunches of questions you can ask, and if you're doing any kind of marketing thing, this is the kind of thing you ask, and then you need to analyze the data, and so Venn diagrams are very useful ways to do that. So, our universal set are the 200 Math 196 students who were surveyed. Right? And we're interested in subsets of them. We'll say A, that's the 170 who like chocolate. B is the 130 who like vanilla ice cream. So what's this one? That 120 people. Well, the people who like chocolate and who like vanilla. So A intersection B is 120 who like vanilla and, there's no N at the end of vanilla, and chocolate ice cream. Okay, so we will need to be able to display this data in this particular way, and a Venn diagram consists of a large box, and the box is for our universal set U, and that's the 200 students that we have surveyed. And then inside we put two circles. Right? One represents A, which is the chocolate people, chocolate, and one represents B, this is our vanilla people. Great, so graphically, what are we looking at? B is this set. A intersection B, those are the people who like both. Well, if you think of, this box being filled with 200 students standing around, and you make the 130 who like vanilla stand here, and the 170 who like chocolate to stand there, then how many are standing in both the circle for vanilla and the circle for chocolate? Well, that's A intersection B. So that's the 120 who like both. So the overlap between the two circles, that's A intersection B. Great. So what's this? Well, that's everybody who likes vanilla and does not like chocolate. Right? If you like both vanilla and chocolate, you'd be here. So the people here are people who are outside of the chocolate circle, so they don't like chocolate, but they're inside the vanilla circle, so they like vanilla. How many people are standing there? Well, in the entire vanilla circle, there's 130. 120 of them are already standing here, so there must be only 10 there. So 120 people like both, plus 10 people who like vanilla, but not, remember not goes with complement, not chocolate. Those are standing there. What about this circle? Well, that's everybody who likes chocolate and who does not like vanilla. How many people are there who like chocolate but not vanilla? Well, there's 120 people who like both. How many people in the entire chocolate circle? 170. If we've already calculated 120 of them, then there must be 50 sitting there. Great. So what's this last area? The area outside of the two circles, but still inside of our box. Well, there's 200 people total. How many have we counted for? 120, 170, 180. So there must be 20 people out here. And what is their preference about ice cream? Well, they don't like vanilla, because if they liked vanilla, they would be inside this circle. And they don't like chocolate, because if they like chocolate, that would be inside this circle. So that's A prime, right? Not chocolate likers and not vanilla likers. So there's 20. So that's how a Venn diagram breaks down. Can we answer some of these other questions? How many like vanilla but not chocolate? Vanilla and not chocolate. Well, vanilla and not chocolate is B and A prime. So vanilla and not chocolate, that's this group. 10 of them. Chocolate and not vanilla. that would be A intersection B prime, right? Everybody who likes chocolate but not vanilla, that's just this part. So there's 50 of those. How many like neither? Well, there's 20, right? There's 20 people who like neither chocolate nor vanilla. How many like chocolate or vanilla? Chocolate. Well, that would be A union B, right? People who like chocolate or vanilla. And that's actually these three people, these three sets added together. So 130 plus 50 is 180 people. Why is that? Well, these people like chocolate, so they like chocolate. These people like both vanilla and chocolate, so they certainly like vanilla or chocolate. And these people like chocolate, like vanilla, but not chocolate, so they like vanilla. So everybody who likes either one or the other or both, that's 50 people like chocolate but not vanilla, 50 people like vanilla but not, 10 people like vanilla but not chocolate, and 120 like both, so 180 total. So these three together is the union, right? The intersection is the part in the middle, and then the other spaces are sort of various complements. Okay, and then finally, a little summation of notation. So if A is a set, we usually use capital A for sets, capital letters for sets. So if capital A is a set, then A with an E there means little a is an element of capital A. It's just one of the things in the list of A. Little b is not an element of A. Right? That means B is something that's not in the list. Right? A subset of A, that means everything in B is in A. Right? And a subset C is not a subset of A. What does that mean? Something in C, can be only just one, is not in A. So not a subset. Okay. If A and B are sets, then A intersection B is everything in both A and B. A union B, everything in either A or B. And then finally, if A is a subset of U, and U usually stands for something called the universal set, then A prime is everything in U that is not in A. And then finally, the empty set, we have a symbol for the set that doesn't actually have anything